Good day, everybody. Today we're going to be starting the physics of the things that are not quite so obvious, and I'm going to start off with the physics of thermal physics, also known as the ability to change the state of matter of something by applying or removing thermal energy to it. So today we're going to be dealing mostly with the states of matter and changing between them. Eventually we'll be moving on to other applications of thermal physics as well. Now, in order to start this thing, I need to go over a couple of the very basics. Now, some of these things you should have gotten in chemistry, and if you did, great, I'm just going to reinforce these. If you did not take chemistry last year, you probably still got this in middle school science, and that's that everything that we have is basically made of atoms. And atoms are made of three major particles. We've got protons, neutrons, and electrons. Now, protons are positively charged. As you can see, I've drawn the little plus sign here. Electrons are negatively charged. It's got a minus sign. And neutrons are neutral. They don't really have a charge. Protons and neutrons hang out in this thing called the nucleus. Nucleus, yay, right there. And electrons are outside of the nucleus, and they hover around randomly oriented in what's called the electron cloud, which is usually just kind of described as having an orbital-like pattern around it. But they don't really spin in circles, they just exist in a cloud. Now, because protons are positively charged and electrons are negatively charged, they naturally are attracted to one another, kind of like opposite ends of a magnet. This attraction is very, very real, and it's what we call the electrostatic force of attraction. Now, this works to keep electrons attached to the protons within the nucleus. It also works if I suddenly add a second proton, or a second atom, I should say, in here. So I've got more protons, neutrons, and electrons. In this case, I've got two different hydrogen atoms. And I'll draw my little nucleus. My lovely electron is circling incorrectly around the outside. And this proton over here now also has an attraction to that electron right there. And this proton right here is also attracted to this electron up here. These two atoms are now stuck together thanks to the electrostatic forces between them. And this is very important because this is really what gives solids and liquids their makeup, because their atoms or molecules are stuck together. It's because of the electrostatic forces between the protons and electrons in their various atoms. Now, to be clear, the electrostatic force is strong. It's not infinitely strong, which is why we have to deal with the second idea, and that's the kinetic energy of particles and how it changes in high energy and low energy states. Now, to kind of illustrate this one, I'm going to draw two boxes that are going to represent cars driving opposite directions on a road. So this one's going that way, this one's going that way. There we go. That's a much better arrow. And we've got two people in these cars that are reaching out and they're attempting to hold hands. Now, if this is a very low energy state, which is right here, a low energy state, these cars are not moving very fast. Maybe they're just kind of half idling with the brakes on. These people are going to be able to hold their hands fairly well, and if they're really, really strong, they may even be able to slow down the car, depending on how strong the car is. However, if we're dealing with a high energy state and these cars are moving quickly, I don't really care how strong the people within the cars are. There is no way they're going to hold these cars together. And this is a really important kind of conundrum in thermal physics, because depending on the speed of the molecules that they're working with, sometimes the electrostatic forces, which I'm representing with the hand holding right here, I'm going to call this the ES force, sometimes our electrostatic forces are strong enough to hold the molecules together and they get clumped up, and this is what we refer to as a solid or a liquid state. But every once in a while, you've got a high energy state where it doesn't matter the strength of the electrostatic force. These things are going to fly apart, and when these molecules start flying around in their container, that is our gas phase. So, different states of matter. All substances exist as either solids, liquids, or gases. Every once in a while we have to deal with something called a plasma. However, that and most plasma physics are outside of the range of high school courses. But just know that plasma states do exist. It's basically a gas on steroids. So, solids. In a solid, particles basically vibrate around a fixed position. They're not moving very much. They just kind of sit there, and they might let's see, I'll just draw a little solid right here. This is a solid particle. It might move a little bit this way, and then it'll move back this way. Maybe it'll go this way. Maybe it'll go this way. It never goes very far, and it basically always returns to its starting point. It always has a displacement, I should say, of 0. It vibrates around a fixed position. These particles get very closely packed together. Their electrostatic forces are very strong in a solid, and they kind of hold everything together. So the particles do not move between other solids. If I move two different blocks and they are now touching, all of a sudden they're not exchanging atoms between the blocks. They stay within their defined solid, which means that solids have a defined shape and a fixed volume. Your volume of a solid does not randomly change unless we apply a huge amount of energy to it. Liquids are slightly different. A liquid is a more high energy form of a solid, or when a solid is heated, it may form a liquid. In a liquid, the particles or the molecules move in between each other, and they are approximately the same distance apart as a solid. So they're still clumped up just about as tightly together as in a solid, but they have a little more energy and they move around more freely. So a liquid does not have a definite shape. It will slosh around to fill its container. However, its volume doesn't change. If I have 100 milliliters of water, I will still have 100 milliliters of water pretty much regardless of what I do to it outside of having it evaporate. Now, gases is the last one that we talk about. Gases are the highest energy state barring plasmas. Gases are a high energy state, and this is what happens when a liquid is heated. It may evaporate or boil to form a gas. So these are only the highest energy particles in our gas, and they move extremely fast. There's a lot of distance in between them, much further apart than a liquid or a solid. And the gas will basically bounce around and attempt to fill the shape or volume of its container. So it does not have a defined shape and it does not have a defined volume. So first thing I want you guys to do in your notebook, please fill out the following table and fill in the blanks as being either yes or no for each one of these things. So does it have a definite shape? Is it easily compressed? Does it have a defined density, which is how much stuff is packed into a certain amount of area? Does it flow or does it move kind of like a fluid, or is it stuck in a single form? Does it expand to fill its container? And does it have a fixed volume? Go ahead and answer yes or no for all of those things. And that's going to be the first thing that I look for in your notebooks. So we finally arrive at changes in state. How do we change the fact that solids have a fixed volume and a fixed orientation? Liquids have a fixed volume, but they kind of slosh around in their container. And gases, they move wherever they want to, expanding to fill their container. How do we change between the three of them by changing the amount of kinetic energy that those molecules have to break their electrostatic forces of attraction? And so the first thing that we need to do is define what exactly is temperature. And in physics, our definition of temperature is that it's a measurement of the average kinetic energy of the atoms or molecules that make up a substance. So when I have a high temperature, what I'm really talking about is that the molecules or atoms that make up the substance are moving really quickly. That's what happens in a high temperature situation. On the flip side, in a very low temperature situation, those molecules are moving much more slowly. Now, we're talking about kinetic energy. Our definition for kinetic energy, our little equation down here, kinetic energy is 1/2 mass times velocity squared. The mass of our atoms are not changing. So it's important to note that the only thing that changes when we're dealing with the kinetic energy of a molecule, changing it by temperature, is we're dealing with the velocity. And a small change in velocity, because it is squared up here, will lead to a much larger change in kinetic energy. So if you decide that you want to raise the temperature of your food, what you're really doing is you're increasing the velocity that those particles are moving around in your food. So energy. The particles of a solid or liquid possess what's known as kinetic energy, and they also have potential energy, the ability to suddenly begin moving. That potential energy becomes unlocked when you start adding thermal energy to things. To change the state of a substance, energy must be supplied or removed. This means basically I am increasing or decreasing the movement of the particles by changing its heat and pressure. And pressure is going to become an important one, but just a reminder, pressure is basically the force that is pressing down on a substance. So, changes of state happen because all matter can move from one state to another. It may require extreme temperature or extreme pressure, but it definitely can be done. If I want to change glass into a liquid, I can do it. It just requires that I have to get it like 1,000 degrees Fahrenheit in order to pull this off. So extreme temperature and extreme pressure might happen, but changing state can be done. And once again, note that I'm not just dealing with temperature, I'm also dealing with pressure here. So I can change something, I can change a liquid into a gas by removing pressure and basically putting it into a vacuum, and it will boil on its own. So it's not just temperature that we can manipulate in order to change states. The less kinetic energy a molecule has, the more likely it is going to stay near other molecules due to their electrostatic forces of attraction. So if I've got two really slow water molecules, my H2Os here, if they are moving really slowly, they're going to have this electrostatic force of attraction between the two of them. And my ES is once again kind of my electrostatic forces. I'll add the word forces just so nobody gets confused. So if they're moving really slowly, they have a very low kinetic energy, these two are going to get stuck together and water forms ice when it's a really low temperature. However, if I start raising the amount of kinetic energy and these things start moving quickly and far away from one another, these electrostatic forces will break, and all of a sudden I've got a liquid if they're moving a little bit faster, and you get a gas if they're moving a lot faster. And this happens when I change their kinetic energy, and in order to do that, I have to increase their temperature. So, having said that, what is the difference in the molecules of an ice cube and liquid water? This is going to be the second kind of free answer question that I'm going to be looking for when I'm grading your notes. Moving on with that, boiling versus evaporation. So there's two ways that we can get a liquid water, or any liquid for that matter, into a gas state. One of them is boiling, one of them is evaporation. For a given pressure, there is a temperature above which a liquid cannot exist in liquid form, and this temperature is called its boiling point. So basically, if you have the standard pressure of a room, which is around 100 kilopascals, and that pressure is pressing down on your liquid, if I provide enough energy to the liquid, eventually those molecules will have enough energy that they can break out of the pressure that's pressing down the liquid and join the air as a gas. And that temperature is what we call the boiling point. Boiling point changes based on how much pressure you're submitting the liquid to. So at this pressure and at this temperature, if the liquid is heated up, the temperature will not rise. And I kind of underline this as a really important thing. I'll draw a box around it because, once again, I want to emphasize how important this is. If you have a liquid that is at its boiling point and you see it boiling, you can continue to add all the energy to that liquid that you want. You will never get it to rise above its boiling point. All you will do is successfully get it to boil faster. So if you get water to boil on a stove and you try to keep turning the heat up, that thermometer is never going to go above 100 degrees Celsius. It's going to constantly stay there, but you can get it to boil off faster. So at this point, the heat is only being used to convert the liquid into its vapor, and this is the process called boiling, where you're using temperature to convert a liquid into a gas. So, just kind of a quick summary of evaporation. Evaporation can only happen at the surface of a liquid, and this is basically just a couple high energy particles at a time. Remember that temperature is a measurement of the average kinetic energy. So that means that at any given moment, some molecules of water are going to have higher energy than other molecules of water. And the really high energy ones might be able to reach the correct amount of energy to evaporate and be able to leave the liquid. So this happens all the time, and it only happens at the surface of a liquid. This takes a lot longer, obviously, because there's a lot less energy in the system. So it is possible for an entire cup of water to evaporate. It's going to happen a lot slower than if you were to boil the cup of water away. So once again, evaporation happens only at the surface of a liquid because the molecules are moving the fastest there. Also because this molecule right down here has all the added pressure of all these molecules on top of it also weighing it down. whereas this molecule right here doesn't have any of that added pressure, so it's free to just simply fly off as soon as it reaches the correct amount of energy. So, in summary, evaporation happens only at the surface of a liquid because that's where molecules are moving the fastest due to temperature and pressure. Boiling happens when molecules throughout a liquid reach the necessary amount of energy to change the state into a gas. This is why when you boil water, you can see bubbles that'll start at the bottom of your cup and move upwards, because when you've reached the boiling point, any molecule in that might spontaneously turn into a gas. It's not just the ones at the surface anymore. All right, so now that we've covered phase changes moving between solid, liquid, and gas by manipulating the kinetic energy of something, we can talk about temperature conversion. And this is the much more practical application that you're looking for if you're looking for just some easy math to run around and look fancy with. There are three different ways that temperature is measured. In America, we measure it in the Fahrenheit system. Pretty much everywhere else on Earth, it's measured as temperature Celsius. And in science, we measure something in what's called degrees Kelvin. Now, important to note, in degrees Kelvin, there is nothing that reaches negative temperatures. 0 is your lowest temperature when you're dealing in degrees Kelvin, because once again, temperature is talking about the average kinetic energy of a substance. So in theory, if the molecules in your substance are not moving at all, that would be a temperature of 0 in Kelvin. So 0 degrees Kelvin is not even, it's only theoretically possible. We can never actually get something to 0 degrees Kelvin, but it basically means that all molecular motion has stopped, which means everything is dead. So just to clear up, there is no negative degrees in Kelvin. Celsius scale, on the other hand, is kind of created around the boiling and freezing temperatures of water, which 100 degrees or 0 degrees respectively. And Fahrenheit, I am not 100% sure why the Fahrenheit scale is the way it is, but for some reason it's really popular in the United States. And we need to know how to convert between the three of them. So this chart right here will help you out. This is a Fahrenheit, Celsius, Kelvin, and how to interchange between the three of them. Now, the last thing I want you guys to add to your notes as far as free response questions, convert 32 degrees Fahrenheit to Celsius and Kelvin, and then convert 100 degrees Celsius to Fahrenheit and Kelvin. So hopefully that isn't too difficult using the chart that you found on the previous page. And then the last thing I want to talk about is the point of change. Freezing water happens at 0 degrees Celsius. Any lower than that, and you're just, once again, you're increasing the rate that something freezes, but you're never going to get ice any colder than 0 degrees Celsius. It doesn't happen. Boiling water, 100 degrees Celsius. This is the temperature at which liquid begins to change into a gas spontaneously on its own. Remember that evaporation can happen at any temperature. So this is just specifically the boiling point. Evaporation happens all the time. Evaporation at any temperature. And then finally, average room temperature in Celsius, because we're not familiar with Celsius, the average room temperature hovers right around 21 degrees Celsius. And if you really wanted to convert that into Fahrenheit, you're more than welcome to using the tools I've already given you.